Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. Today we will discuss on locally compact spaces. During last 6 clips, we have discussed 4 kinds of compactness, their relation to each other, their equivalence in some particular spaces, and we have also characterized them. You may be feeling bored hearing that I am bringing one more new kind of compactness to you, but think none of the well-known spaces like R, Rn, even space of complex numbers enjoys none of such 4 compactness, though every closed and bounded subset of them are compact, and so sequential compact, limit point compact, as well as countable compact, because all of them are metrizable. Today in this 7th clip we will see all such familiar spaces are locally compact, and that concept of local compactness is defined by the help of such compactness. So let's begin with the very definition of locally compact spaces. So the definition: a topological space is called locally compact. It's called locally compact if each point of it has a neighborhood base consisting of compact sets. That is, a topological space X will be called locally compact if for every point small x of it has a neighborhood base beta x whose members are compact sets. So members of this beta x are compact. So, and this beta x is a neighborhood base. It means if U is any neighborhood of x, then there exists a member B in beta x which is totally contained in U. This is the definition of neighborhood base. Any neighborhood of x will contain a member of beta x. Okay. In addition to that, the members of beta x are compact sets. Okay. Fine. So let's see some examples of locally compact spaces that can be checked from this definition directly. So first example is R with usual topology. Okay, fine. So this R with usual topology is locally compact because if x in R, then beta x equal to collection of all those compact subsets of the form x minus 1 by n, x plus 1 by n closed interval, where n in the set of natural number. This is a neighborhood base, you can check easily. This is a neighborhood base consisting of compact sets, because every member is compact, being closed and bounded subset of R. Another example is Rn with product topology or box topology. Or you need product topology. Okay, this is also locally compact. For let x equal to x1 x2 dot 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 xn, this any member of Rn, then beta x, which consists of this kind of members, where x1 minus 1 by m, x1 plus 1 by m closed interval cross x2 minus 1 by m, x2 plus 1 by m cross dot 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 cross xn minus 1 by m to xn plus 1 by m. Okay, is that m in set of natural number. Okay, here every member of this beta is also compact because every factor is compact. So by Tikhonov theorem, this product is also compact. Okay, and it is also a neighborhood base. Then this is a neighborhood base at x consisting of compact sets. Okay, and in particular the space of complex numbers with usual topology that we use in complex analysis with usual topology is also locally compact, because let A in C, then this beta A is the collection of all sets of the form this Z in C, such that mod of A minus Z less or equal to 1 by n. Okay, where n in the set of natural number. Actually this is nothing but the closed ball centered at the point A having radius 1 by n. Okay, so this being closed and bounded, it is also compact. So this beta A is a neighborhood base at the point A consisting of compact sets. Okay, so R, Rn, C all are locally compact. Okay, but don't think that every space is locally compact. Okay, I am returning back to show the existence of non-locally compact spaces, just proving one important result. Okay, which will make easy to check whether a Hausdorff topological space is locally compact or not. Okay, so the result is this. This is important result. A Hausdorff space, Hausdorff means T2. A Hausdorff space is locally compact if and only if each point of it has a compact neighborhood, has a compact neighborhood. So in case of Hausdorff space, it is not necessary to check whether every point of it has a neighborhood base, okay, consisting of compact sets or not. Just if we show that every point has just one compact neighborhood, then we can conclude or we can declare that Hausdorff space is, that particular Hausdorff space is locally compact. So let me sketch the proof, sketch of the proof. One part is very easy, that let X be Hausdorff and locally compact. I am assuming that it is locally compact. Then each point of it has a neighborhood base consisting of compact sets. That neighborhood base consists of compact sets. So all those neighborhoods of that point are compact neighborhood. So every point of this space has plenty of compact neighborhoods, roughly speaking. Okay, at least one compact neighborhood will be there. So every point of X has a compact neighborhood. Okay, so if a Hausdorff space is locally compact, then every point of it has a compact neighborhood. So this part is done. Now converse part. So let X be Hausdorff and every point of it has a, say every point X in capital X of it has a compact neighborhood K in X. Okay, we will find a neighborhood base at X consisting of compact sets. Okay, so let beta X be the collection of all compact neighborhoods of that point X. Okay, then this beta X is, since this K is a compact neighborhood of this point X, so K in beta X, so therefore K in beta X, and this implies this beta X non-empty. Okay, we will show that this beta X is a neighborhood base at X, and members of beta X by the construction of beta X are compact sets. Okay, so just it remains to show that beta X is a neighborhood base at X. Okay, we need to show there exists a neighborhood base at X whose members are compact sets in order to show the space X is locally compact. No, by definition. So this beta X consists of compact sets by this construction. Okay, so just it remains to show that this beta X is a neighborhood base at X. What does it mean? We will take any neighborhood U of x, and we will find a member in beta x which is totally contained in U. Okay, so let U be any neighborhood of x. Okay, then we know that finite intersection of neighborhoods is also a neighborhood of the same point. Okay, since k and u both are neighborhoods of x, so k intersection u will be neighborhood of x. It is very easy. K is a neighborhood of x, so there exists an open set say O1 containing x and which is totally contained in K by the definition of neighborhood. U is also a neighborhood of x, so there exists an open set O2 say totally contained in U which contains x. So if you take intersection, then x belongs to O1 intersection O2 totally contained in K intersection U. So this K intersection U also contains an open set. This is finite intersection of open set is open. So this K intersection U also contains an open set containing this point x. Okay, so this is also a neighborhood of x by definition of neighborhood. Okay, now from this it is clear that if we consider infinitely many neighborhoods of x, and if we take their intersection, this intersection may fail to be a neighborhood of x, because as simple as that, here we will get infinite intersection of open sets contained in that infinite intersection of neighborhoods, but this intersection of infinitely many open sets may not be open, you know. Okay, so that intersection of infinitely many neighborhoods may not be neighborhood of x. Okay, so finite intersection of neighborhoods of x is also a neighborhood of x. Fine. So this k intersection u, this is a neighborhood of x. This is a neighborhood of x. Okay, this is a neighborhood of x. So there exists an open set. So there exists an open set O in x such that x belongs to O, which is totally contained in K intersection U by the definition of neighborhood. Okay, now if we take interior, so x belongs to O, interior is O, subset of K intersection U, interior. Now this subset of K intersection U, interior, closure. Okay, fine. Now this K intersection U, this is a subset of K, of course. Okay, so we can write this subset of K bar. Why? Just this K intersection U subset of K, and this K intersection U interior is a subset of K intersection U. So K intersection U interior subset of K. So K intersection U interior closure subset of this closure, So this is subset of K bar. Also, this is the place where I will use the Hausdorff property of x. Okay. How? Since x is Hausdorff, right? And K is, what is K? K is compact neighborhood, that is K is compact. K is compact subset of X. So K is a compact subset of a Hausdorff space. So K is closed. So K bar equal to K. Fine. Okay. Okay. So this being an open set totally contained in this. So this is open set in X. Okay. So this intersection this will be open in this, but this is a subset of this. So this intersection this will be again this. So this is open in this. Okay. This is open in this, and this contains X. Okay. So this K intersection U interior, this is an open neighborhood of X in this K intersection U interior closure. Okay, let me call it R. Okay, R say, not the set of real number. Okay, this is just the English letter R, capital. Okay, and this R, look at this. This is a closed subset of a compact set K. So this is compact. Okay, that is R is compact, and the main space, underlying space X is Hausdorff, and Hausdorff property is hereditary. So this subspace also Hausdorff. So this is compact as well as Hausdorff. Okay. So R. So this which is compact and Hausdorff. Okay, so T4 and hence regular. So this R is regular. Okay. Now we know that a topological space X, a topological space is regular if for any open set this and any point inside it there exists an open set containing this point whose closure contained in this open set. Okay, now consider this as R. These are okay, and look at this K intersection U interior. Say this is K intersection U interior. So this is an open set in R. Okay, open in R, and it contains small x, this being a neighborhood of X. So this point is X. So we will get another open set in R. Okay, containing this X and whose closure in R totally contained in this interior, this open set, isn't it? Okay, so okay, so there exists an open set W in R, these are okay, such that X belongs to W and closure of this W in R Okay, totally contained in this open set K intersection U, this interior. Okay, fine. And so since closure of W contained in this, so W also contained in this, so W contained in K intersection U interior. Okay, and this implies that W intersection this set is W is open in R, so W intersection this is open in this, W is open, this is a subset of R. Okay, so W is open in R, so W intersection this will be open in this, but W intersection this is W itself, so W is open in this. Okay, this implies W is open in K intersection U interior, and this K intersection U interior open set in X, this is open in X, so W is open in this and this is open in X, so W is open in X. Okay, so W is open in X. This is very, very important. Okay, now almost done. So W is open in X. It is important. Thus we get an open set W in X such that X belongs to W, and W totally contained in, of course, closure in the W, closure of W, of course, larger than W. Okay, fine. So this is a subset of X because whole set is X. So this is a subset of X which contains an open set in X. Okay, and this open set also contains X. So this is a neighborhood of X in X. So this closure in R of W is a neighborhood of X in X. Okay, so for the few seconds we confine ourselves within R. R means K intersection U closure, K intersection U interior, its closure. Okay, and the X is the bigger one. So for the time being we state here to use the regularity of R, isn't it? I have mentioned here this R is compact and housed up, so T4 and hence regular, and by regularity we get open set W and blah blah blah. Okay, so to get this open set we confined ourselves within this for the time being. Now we are coming out from this, and we now present here in the main space X. Okay, So this is a neighborhood of x in x. We arrived at the whole space x ultimately. Okay, so not only that, look at this. Look at this. Right. This one. Closure R. Okay, let me write. Also, this closure of W in R, this is a subset of K intersection U interior. Okay, and of course this is a subset of K intersection U interior bar, that is R, and this R is compact. R is compact. This R, I am talking about this R. R is compact. Fine. So this is closure. So closed. So closed subset of a compact space is compact. So this implies this closure of W in R is compact. Okay, and it is a neighborhood of small x. Okay, fine. So this closure of W in R is a compact neighborhood of x. Compact neighborhood of x. So it belongs to beta x, because our beta x is the collection of all compact neighborhoods of x. Okay, so this closure will be in beta x. Fine. Not only that, look at this. Oh, again, this closure of W in R, subset of K intersection U interior, and this interior always subset of the underlying set, and this is subset of U. Okay, so this also contained in U. So ultimately what we are getting, that for any open set U, or any neighborhood U of x, for any neighborhood U of x, we are getting a member, this in beta x, which is totally contained in U. Okay, and which is a neighborhood of x. So beta x is a, so this beta x is a neighborhood base at x, and it contains compact sets by construction, and it contains, or it consists of compact sets. Okay, so for every point small x, of capital X, we are getting a neighborhood base at x, okay, consisting of compact sets. Okay, so x is locally compact by the definition of local compactness. So the result is proved that the Hausdorff space is locally compact if and only if each point of it has a compact neighborhood. Now this result has some consequences, very interesting and important consequences. So let me write it as corollary of this result, that every compact Hausdorff space every compact Hausdorff space is locally compact. Every compact Hausdorff space is locally compact. Okay, why? Very easy. Because say this is a compact Hausdorff space. Okay, compact Hausdorff space. Okay, the whole set is always open. So whole set is always a neighborhood of any point of it. So take any point small x. Then this capital X is a neighborhood of x, and it is compact. So this x, this capital X, is a compact neighborhood of each of its point, and the space is Hausdorff. So by the result, just proved few minutes back that a Hausdorff space is locally compact if and only if each point of it has a compact neighborhood. So here capital X itself a compact neighborhood of each of its point, and the space is Hausdorff. So by the result proved that compact Hausdorff space is locally compact. But the converse is not true. We have seen already R with usual topology. It is Hausdorff and it is locally compact, but we know it is not compact. So compact Hausdorff space is locally compact, but locally compact Hausdorff space may not be compact. Okay, fine. And this result also has another consequence that will be used to prove some result. Okay, so another corollary is a Hausdorff space is locally compact if and only if every point of it has a relatively compact neighborhood. Relatively compact set means whose closure is compact. For example, open interval 0, 1 in R with usual topology. It is not compact, but if we consider its closure, it is closed and bounded subset of R. Okay, then it is compact. So this 0, 1 open interval is relatively compact. Okay, fine. So this corollary says that a Hausdorff space is locally compact if and only if every point of it has a relatively compact neighborhood. Okay, it is also very easy, because say this is the Hausdorff space. Okay, X be a Hausdorff space. Now if it is locally compact, then nothing to do actually. If it is locally compact, then for every point X, by the last result, every point X has a compact neighborhood, so Cx compact. Now if we consider Cx bar, okay, so this is a closed, okay, Cx bar contains Cx, okay, and Cx is a neighborhood of X, so Cx contains an open set containing X. Fine. So this Cx bar also contains an open set containing X. So this is also a neighborhood. This is also a neighborhood of X. Actually, superset of any neighborhood is also a neighborhood of that point. Okay, in this way we can prove. So this is also a neighborhood of x, Cx bar. Now Cx is compact subset of a Hausdorff space. So Cx is closed. We know compact subset of a Hausdorff space is closed. So Cx is compact subset of this Hausdorff space. So Cx is closed. So Cx bar equal to actually Cx. Cx is compact. Okay. So Cx bar is also compact. So Cx bar. Okay, from these also we can say easily that Cx bar is a compact neighborhood of x. Cx bar equal to Cx. Since Cx is a neighborhood, so Cx bar is also a neighborhood. Okay, and since Cx is compact, so Cx bar is also compact. Okay, so Cx bar is compact, so Cx is relatively compact. Okay, so every point has a relatively compact neighborhood. Okay, very easy. Okay, sometimes we confuse to prove a very easy task. That's happened here. Okay, now the converse part. Let x be Hausdorff. X be Hausdorff. Okay, and assume that every point has a relatively compact neighborhood. Okay, every point has a relatively compact neighborhood Rx. Relatively compact. So that this Rx bar is compact. Fine. Okay. So we have to show that this space is locally compact. No? Yes. We have to show the space is locally compact. So this is Hausdorff, and every point of it has a relatively compact neighborhood. Okay. Okay. So Rx and this Rx bar is a superset of Rx. Rx is a neighborhood of x. Same thing. So there is an open set containing x and contained in this Rx. So Rx bar is also a neighborhood of x, and it is compact. So every point has a compact neighborhood. So the space is Hausdorff, and we see that every point has a compact neighborhood. Okay, so by that result that we have proved, okay, the space is locally compact. So very easy consequences. Okay, so by using this result we can easily say that this R with usual topology is locally compact easily, isn't it? So let x in R, for every x in R, this x minus 1, x plus 1, this is a compact neighborhood of x, because this contains an open set x minus 1, x plus 1 containing x. This is a compact neighborhood of x, and R is T2. R is Hausdorff. T2 means Hausdorff. Okay, R is Hausdorff, and every point it has a compact neighborhood. So by using that, similarly in case of Rn, okay, for every x equal to x1, x2 dot xn in Rn, this is a compact neighborhood of x, x1 minus 1 by n, x1 plus 1 by n, cross dot cross, xn minus, let me write it m, because it may confuse you with this n. So xn minus 1 by m, xn plus 1 by m. This is a compact neighborhood of this point x, and Rn is how it of. Okay. So in this way, but if we consider another example, R omega with product topology, R omega with product topology. The R omega with product topology is not locally compact. Is not locally compact. Okay. Is not locally compact. For the R omega is Hausdorff. R omega is Hausdorff. No doubt about it. No doubt about it, because Hausdorff property is productive property, and R is Hausdorff. R with usual topology is Hausdorff. So R cross R cross R cross. R omega means denumerable product of R with itself. The R cross R cross R cross R cross endless. Okay, with product topology. So this is Hausdorff. No doubt about it. Okay. Now this is Hausdorff, no doubt about it, but no point of this R omega has a compact neighborhood. Okay, why? Okay, because if x in R omega has a compact neighborhood, say n, okay, compact neighborhood n, then there exists a basic open set. So B, you know how the basic open set in product space looks like. Basic open set B equal to, since it is denumerable product, so we can use n. So n in n, where these bn's are open in R, and you know bn equal to whole R for all n not equal to n1 n2 dot nk, say. That is all but this finite number of factors are whole set R. Okay. No. Okay. So this n being a neighborhood of x, there exists a basic open set, this B looks like this, such that this B totally contained in n, and x belongs to B by the definition of neighborhood. Now this implies this pi n B subset of projection, nth projection, pi n for all n in n. So this implies pi n B means Bn, isn't it? So Bn subset of pi n for all n in this. Now if we assume n not equal to this, then Bn will be R. So R cannot be subset of this, so R equal to pi n for all n not equal to n1 n2 dot nk. Fine. What does it mean? It means This implies pi n continuous and n is compact. Okay, n is compact neighborhood, so compact. Fine. So pi n is continuous. We know projection maps are continuous. So this is a continuous image of a compact set. So this is compact. So R becomes compact. So this R is compact. R is compact. Which is a contradiction we know. R with visual topology is not compact. Which is a contradiction. Okay. So if we assume that a point X of R omega has a compact neighborhood, we arrive at a contradiction. So no point of R omega has a compact neighborhood. Okay. And so R omega with product topology. R omega with product topology is not locally compact. Now what about R omega with box topology? You know box topology? And in that case, in case of box topology, the basic open sets looks like just product of open sets. This condition is not there, isn't it? So all the factors may be proper open sets. Okay, that is 0 1 cross 0 1 cross 0 1 cross 0 1 dot dot. Okay, this is also a basic open set in R omega with box topology. Okay, and actually for this reason this R omega with box topology is locally compact. Okay, here R omega with product topology is not locally compact because of this contradiction, no? And this contradiction comes because this Bn is R, all but finite number of indices, this Bn is R. But since there is no restriction in the basic open sets in case of R omega with box topology, so that for that reason this R omega with box topology will be locally compact. It's very easy. Okay, this is note R omega with box topology. R omega with box topology is locally compact. For what? For let x equal to xn in R omega. Okay, then this product, this cx equal to this product of xn minus 1 by xn minus 1 xn plus 1, this n equal to 1 to infinity. Then this is a compact neighborhood. This is a compact neighborhood of x. Okay, this is a compact neighborhood of x. Okay, since R omega is Hausdorff, so by the result proved few minutes back, the space is Hausdorff and every point has a compact neighborhood, so this is locally compact. R omega is Hausdorff because Hausdorff property is productive property and R is Hausdorff, so R cross this is also Hausdorff. Since R omega is Hausdorff, so R omega is locally compact. Fine. Okay, so from this, where it comes, R omega with product topology is not locally compact. R omega with product topology is not locally compact. Though every R is, R means R with usual topology. Every R is locally compact. So product of locally compact space may not be locally compact. So local compactness is not a productive property. So another note is local compactness, but compactness is productive property because we have proved, okay, in some class, okay, not in this YouTube, in the classroom we have proved that arbitrary product of compact spaces is compact. So compactness is productive property, but local compactness is not productive. Okay, so if you are asked to check whether local compactness is productive or not, you have to give the example of this R omega with product topology, and you have to show it is not locally compact, though R with usual topology is locally compact. Okay, and hence local compactness is not productive property. Okay, now let's come to some another point. Okay, every discrete space X is locally compact. Every discrete space X is locally compact because very easy. For let X in capital X, then this singleton X, in case of discrete space every subset is open, so this singleton set is open, so this is an open set containing X, so it is also a neighborhood of X. Okay, and this being finite, so it is compact. Every finite subset is compact. Then this is a compact neighborhood of X, and discrete space is metrizable. The discrete metric is a suitable metric that induces the discrete topology on X. Okay, and every metrizable space is T4, so T2 means Hausdorff, and X is Hausdorff. Okay, so this X is locally compact by that single result that we have proved few minutes back. Okay, X is Hausdorff and every point has a compact neighborhood. Okay, so X is locally compact. Okay, I will conclude this clip by showing another example of non-compact space, which is not of the form of a product. This is nothing but the space of rational numbers as a subspace of R with usual topology. Okay, so another example, the set Q of rational numbers. Okay, we can prove as simple as that the space of irrational number also not locally compact. Okay, I am sketching a proof of this. Okay, so the set Q of rational numbers as a subspace as a subspace of R with the set Q of rational numbers as a subspace of R with usual topology is not locally compact. We know usual topology comes from this metric dxy mod of x minus y. Okay, and Q is a subspace of this. It means this tool will be used to measure distance between any two rational numbers. That is, in Q also dxy equal to mod of x minus y, where x, y rational numbers. Okay, fine. So this set Q of rational numbers as a subspace of R with usual topology is not locally compact. For here also we will see that no point of Q has a compact neighborhood. Okay, for let x in Q and if possible let this x has a compact neighborhood. This x has a compact neighborhood in Q. Mind it, we are in Q. Okay, we are in Q. This is very, very important. Fine. So N is a neighborhood of x in Q. So there will be a basic open set in Q containing x totally contained in N. Okay, so there exists epsilon greater than 0 such that this x minus epsilon, x plus epsilon intersection Q, this is basic open set in R. So this intersection Q, the basic open set in Q as a subspace of R, isn't it? This totally contained in N by the definition of neighborhood. Okay, fine. Now let R in this. R is an irrational number within x minus epsilon, x plus epsilon. Okay, so x minus epsilon, x plus epsilon intersection Q complement. Okay, Q complement means set of irrational numbers. So R in Q complement means R is a rational number and R also in this because intersection is there. So R is, so say this is x minus epsilon, this is x plus epsilon, and R is somewhere like this, and it is irrational. Mind it. Okay, so we know in BSc that set of rational numbers is dense in R. So there exists a sequence of rational numbers converging to R. Okay, fine. So then there exists a sequence xn in this x minus epsilon, x plus epsilon intersection Q okay, which is contained in n, this. So there is a sequence xn in this. There is a sequence of rational number in this. Okay, such that this xn converges to this r in r, because this is not true in n or in q, not true. Why? Because r not in n, r not in q also. Okay, n means not the set of natural number, n means this neighborhood. Okay, xn is a sequence in this n ultimately, but this r being irrational number, it is not in n. Okay, so this xn is not convergent in n or q, mind it, but it is convergent in r, this r, but too small r. Fine. Okay, I will write the same thing, but since r not in n, though this xn is a sequence in n, okay, this xn, actually no subsequence of xn, no subsequence of xn is convergent in n, because xn converges to r in r, so every subsequence of xn will converge to r in r, so no subsequence will be convergent in n or in q, because these are neither in n nor in q. Okay, I tried to write the same, but since r not in n, so though xn is a sequence in n, but no subsequence of xn is convergent in n, so n is not sequentially compact. So n is not sequentially compact, but n is a subspace, n is a subset of q in q. Okay, and q is a metric space, dxy mod of x minus y. So same metric will be used to measure distance between any 2 points of n also, that is n is also a metric space. Okay, so since n is a metric space and it is not sequentially compact, so it cannot be compact, because in a compact metric space all those 4 kinds of compactness are equivalent. Okay, so n is compact but not sequentially compact, it is not possible. So since n is not sequentially compact and n being a subset of a metrizable space q, n is not compact. N is not compact, which is a contradiction. Because we have assumed that if possible let x has a compact neighborhood n. Okay, so n is compact, but here we see that n is not compact, which is a contradiction. Okay, so if we assume that a point small x of Q has a compact neighborhood, then we arrive at a condition. So no point of Q has a compact neighborhood. So Q as a subspace of R, Q as a subspace of R cannot be locally compact. So Q, very very important, Q as a subspace of R is not locally compact. Why I am saying this so loudly, that Q as a subspace of R is not locally compact? Because if we consider Q with the discrete metric, so Q will become a discrete metric space. Here we have assumed that Q with this metric dxy equal to mod of x minus y, that is Q as a subspace of R. Okay, as a subspace of R, we are using the same tool to measure the distance between any two rational numbers as we use in case of two real numbers. Okay, that's why we saying that Q as a subspace of R. Now if we change this distance measuring tool, if we use the discrete metric in Q to measure distance between any 2 points of Q, then we will get discrete topology on Q. So every point will be every subset of Q will be compact. So every singleton will be compact neighborhood. So Q will be locally compact if we consider discrete metric. But if we consider this subspace Q as a subspace of R, we have just proved that it is not locally compact. And just few minutes back we have also proved that every discrete space is locally compact. Where the proof? Just few minutes back we have proved, no? Every here just above this, every discrete space X is locally compact. So if we consider X equal to Q with discrete metric, then it will be locally compact. So this is important, that Q as a subspace of R is not locally compact, and we have proved it, so no doubt about it. Okay, so we will extend this study of local compactness in the next clip. So keep watching. Thank you.